On the 6-phase system, we can take two of the phases that are 120 degrees apart and put a voltage meter across that, and there is the vector diagram of what this machine does. And that's 1/3 of the total half. And then we call that a vector subtraction. That yields 8.8 volts in former circumstances. And then because we have a 6-phase system, we can reverse the wiring and attach the voltage on instead of a 120 degree phase angle, a 150 degree phase angle. This yields yet a larger voltage here. And this longer voltage, since it's a vector addition instead of a vector subtraction, we take the normal vector current in time down here and vectorially add it up here, and making this a vector addition. Respectively, we obtained 9.38 and 8.8 volts in former circumstances. This schematic models exactly what's going on here, but because of temperature differences, it's colder. We don't know why that is on resonance circuits, why they do some of these things, but generally speaking today we'll probably only see 4.4 volts, not no 5 and 4.7. We'll see a lower voltage. But what's going on the same vectorially is the same thing. Now we can see by common sense that this meter here, being across phases number 2 and phase number 1, and that meter there being across phases number 1 and 3, are overlapping the quantity that's in the middle, phase number 1. And we also see that for that reason, we can never add that quantity and expect it to equal that quantity, and indeed those quantities there exceed the unity addition of the 3 voltage magnitudes that they were comprised from. What the remarkable circumstance comes is that we can see situations where the end voltage will in fact exceed the sum of the component voltages. We call that a circuit of oversummed. Okay, what we're going to do is we're going to see that right when we first turn it on. And we got the voltage meter set up over here, and that's what we see without a field. Okay. We'll turn that on now and get the voltage meters set up. The front 3 meters are on the phases themselves. This is a communist system, by the way. What we got, we didn't neglect to state here, is we got the system, the primary system itself converts 3-phase into 6-phase, and on the top we got phase number 1, phase number 2, phase number 3 in that phase rotation. We also have a secondary here, a secondary here over the top poles of 2 and 1, which are shown on the diagram, and we also got a secondary under the red phase number 3 down there at the bottom, and these are wired in series to obtain the highest possible voltage that we can get, which is also diagrammed and shown previously. So we'll turn that on now. What we have in this situation is the first instance of what I've called an Overunity series voltage summation. We should be able to see that we're taking 0.7 volts from each of them. Secondaries that I just showed you, we've got 1.4 volts on the second voltage meter reading right there, primitively showing them close to unity out of phase. And we got that voltage meter not yet turned on. It's reading 1.8 volts with components of 0.7, 0.7. Actually, an idiosyncrasy, which shouldn't be possible from that input voltages because it's over the sum of them. And then finally, we have 2.7 volts totaling on all three 0.7 volt input measurements. That's over the sum of their unity values. So we're in question there. That's a meter problem. So once we turn, this is the conditions we're seeing without the field. Once we turn the field on, all of the ordinary vector mathematics will normalize. So that's what we need to do next. We neglected to show the pre-field conditions on the outputs. Those are 0.8 volts across the board, 0.3 volts across the board on the phase amperages. Now we're going to turn the field on, leave that on the input board. At this level then we're obtaining generally a 5 volt input and with amperages 1.4 across the board. 1.4 amps across the board. Now for the secondaries, we're showing 4.3, 4.5, 4.2 individual volts, showing 7.9 between one, 8.5 between the other one, and a total of 12.78 volts, 12.8 volts, which roughly corresponds to the diagram that we showed in the beginning to what's going on vectorially. Now we want to try to see we're getting close to the end here. We've got to try to show something real quick. So what we're going to do is we're going to short out. We're going to enable a free oscillation to occur on the center coil. Right now there's no output taken. We're just reading voltages. But we also down here have arranged things so that we can at any time extract amperage individually from one of them three in the series chain. And then we're taking the power out in the conventional manner. So what we're going to do is we're going to take that power out in the conventional manner, and it's going to wipe that middle 4.6 volt reading out to zero. Well, it's not supposed to do that. Not at all. I have no clue what's going on here. Maybe that's the wrong one. That's the middle one, all right. I don't know what's going on, folks. Oh, another screw up. Well, the circuit may be working differently. I don't know. You probably don't know why I'm laughing. Right now, all of our inputs went down to 2.4 and 1.6 volts. We got 0 volts between one of them. We got 3.5 between the second two, and we only got 2.3 volts. Let's go back and try something different here. We're running out of time. We already did.